Let's look at some examples that allow us to look at enthalpy and Hess's law a little bit more. So if we have this reaction, these two reactions here, this first one, what's going to happen is ammonium nitrate starts to decompose and it releases energy as long as it's in the presence of both chloride ions and water. So you could mix it with any salt that has chlorine ions in it and then throw a little water in there and it's going to start to decompose. And while it decomposes, it's going to release some energy. Something interesting though is if you place zinc nearby, the products are slightly different. So does this affect the energy release in any way? Let's do some math. Let's look at Hess's law and enthalpy. Let's figure out if and how this energy release is affected. Is it bigger? Is it smaller? Is it the exact same? Well, I'm glad you asked. Let's do some math and figure this out. All right, so here's what we have. We can look up all of these variables in the appendix of our book, except for this first one, which is negative 366. And that is kilojoules per mole and standard enthalpy. So pause the video and look up the enthalpy values for each one of these two molecules in your appendix in your book. You should have gotten 82 and negative 242. So now if we remember our equation that pertains to determining the enthalpy for our entire reaction, we look at the enthalpy change for the products as compared to the change in enthalpy for the reactants. And so when we're doing this, we take our products, which are these two over here, and we list them, but remember we need to take into account the number of moles. So we have 1 mole of our N2O times our 82, and that's kilojoules per mole, plus 2 moles of water times negative 242 kilojoules per mole, minus 1 mole of our ammonium nitrate times negative 366 kilojoules per mole. And if we put all of that into our calculator, we end up with negative 36 kilojoules. So definitely exothermic, going to release energy, but is this a big number, small number? It's all relative. Okay, so some energy release, but what happens if we throw zinc in the mix? So same thing, same decomposition of ammonium nitrate, but as we're breaking it apart into smaller entities, we're doing so in the presence of zinc. Is that going to change the amount of energy that's released? Well, I'm glad you asked. Let's look and see. Once again, look up the enthalpy values for each one of these in your textbook, making sure you know how to do that step. All right, so you should have gotten the above values of enthalpy for each one of our molecules or atoms. So now we go products minus reactants. So products first. So I'm going to go 1 mole of nitrogen times 0 plus 1 mole of zinc oxide times negative 348 plus 2 moles of water times negative 242. Now I subtract out all of my products. So minus a negative 366, and that was times 1, so negative 366, and then also minus our zinc, but it's going to be 1 times 0, so it's not really going to matter. All right, so we've subtracted both of our reactants from all of our products, and we end up with negative 466 kilojoules, and that is our enthalpy at standard conditions for this reaction. So is that bigger than before? Absolutely. So by adding in zinc to this, it changed the products and we released a whole lot more energy. And so when we think about this and we do a demo that maybe does this, we'll be able to tell how big is the reaction, what's happening, does it look like heat's being released, can you feel that heat being released, that kind of thing. But yes, you will definitely release more energy if you put it in the presence of zinc. So this is a summary slide just showing us the relative energy release of the two equations. Let's do another example. So this is a similar type of problem, but this time we're going to look at the stepwise formation of our sucrose. So we know that, or dehydration, excuse me. So in this example, we're going to look at the dehydration of sucrose in a stepwise manner. So instead of looking up all the individual components, we're instead going to use these first two reactions that have known indicated enthalpy values to try to determine the enthalpy for the dehydration of sucrose, which we see right down here in this last and final equation. Okay, so if these are our known values and we're trying to come up with this goal, we're trying to make this equation down here. How do we do that with these known things? Well, with Hess's law, it says you can combine things in small steps to create the whole. And so in this case, we can look at each of our different equations and decide how do we need them, what do we need to go forward to create this whole final reaction. Now, what do I mean by that? All right, I know I need C12H22, and I've got one of those in this equation, just like I have one of them in this equation. Now I need 12 carbon. 12 carbon, where is that? Well, it's here. It's on the wrong side, so that tells me I'm going to need to move it. I'm going to need to flip the whole equation. And there's only one of them, so I need to multiply this equation by some number, and that number being 12 because I want 12 of them. But before I do that, I want to check and say, hey, do I have enough water? So where's my water? It's right here. Hey, what do you know? It already has 11. So in that case, I'm just going to be working with this and seeing if it balances. So let's flip it and multiply it by 12. So 12 carbon dioxides yields 12 carbon in the form of graphite, that's just like your pencil lead, plus 12 oxygens. And because I did that, because I multiplied each of my substances by 12, I also need to multiply my delta H reaction by 12. So that gives me 4,722 kilojoules per mole. Well, what about my sign? This one's negative. When you flip, you need to flip the sign. So we're going to flip the sign as well, making this now positive. So now I need to see, does anything cancel out? So now I'm going to ask the question, does anything cancel out? So we're just looking at these two equations right here. And we're saying between these two, can we add them together in some way so that way we equal our goal, that being this equation right here? Well, let's see. We have 12 oxygens on this side and 12 oxygens on this side of the arrow, so they are going to cancel out. I have 12 CO2s here and 12 CO2s here, so 12 carbon dioxides will cancel with 12 carbon dioxides. Do I have anything else that can cancel? We have sugar here. That doesn't have anything on the other side. We have water and we have graphite. So if we bring all of these values down, we're going to have C12H22O11 as a solid plus, yields 12 carbons in the form of graphite plus 11 waters in the form of a liquid. And that matches our goal exactly. So that's exactly what we wanted. Now what do we do with our enthalpy values? So remember, this enthalpy value here is associated with this reaction, and this enthalpy is associated with this reaction. So we just need to add these two values together to give us a final enthalpy value of negative 918 kilojoules per mole, and that's per mole of our reaction. So in this example, we used a stepwise process to get and to determine the enthalpy of the reaction. And so in this case, you sometimes have to flip equations, sometimes you need to multiply them by a number, but whatever you do to the equation, you need to do also to the value of the enthalpy for that specific step. And if you flip it, you flip the sign that accompanies that enthalpy value.